This is GM Word of the Week, and I'm Fiddleback. Volcano. We here at the Word of the Week, as we mentioned last week, are accomplished survivalists of the highest order in video games. We've negotiated every conceivable hazard the natural, unnatural, metanatural, and supernatural world has ever seen fit to throw at us. Well, throw at our little electronic avatars. And of all the many hazards we've survived unscathed, the one we've dealt with the most is lava. We've dodged, jumped, flown, skipped, driven, and even swam over and through miles of that deadly, bubbling crimson fluid, with the appropriate power-ups. And as such, we are intimately familiar with the stuff. Thus, we can tell you categorically that lava is a red, water-like fluid found primarily underground and in medieval castles, but occasionally also flowing freely above the ground. It gathers in pits and tends to remain stationary. It's always bubbling like boiling water, and it is completely harmless unless you are entirely immersed in it. Whereupon, assuming you don't have the appropriate power-up, it is instant death. Right? Well, occasionally even video games get it a little wrong. The problem isn't that video games get it wrong, though. The problem is that they also get it a little right. And you only find out what they get right and what they get wrong when something spectacular and chilling and terrifying and tragic happens, and when something that by rights should only exist in a video game suddenly bursts off the screen and into the real world. At the time of writing this script, we've been watching an actual active volcano eruption for 2 months straight. For the record, in case you're listening in the future, it is the end of June in the year 2018, on the planet we call Earth, in roughly the third populated orbital around a small, yellow, well, you probably know already. At the start of May, about 2 months ago, the largest island in the Hawaiian archipelago, Hawaii, aka the Big Island, was rocked by a series of large earthquakes. Soon thereafter, an explosion of lava gave forth from the Kilauea volcano and sprayed into the Puna residential district, forcing an immediate evacuation of residents. Then a massive crack opened up in the ground of the Leilani Estates subdivision, and steam and molten lava came pouring forth. Several craters and vents that were part of the volcano collapsed, forming larger, more massive craters, and the volcano has been erupting from various vents and craters since then. Lava is pouring from at least 4 different sites as we speak, snaking its way across the island and into the sea, changing the shape of the land and devouring everything it touches. Earthquakes continue to rumble across Hawaii, craters continue to expand, and as of a few days ago, a U.S. geological research station was left teetering on the edge of a massive crater, which is still expanding and doubtless will swallow the station. Thousands have been evacuated. And yet, very few people have been injured or killed. Seems amazing, doesn't it? Don't get us wrong, the devastation is horrific, we're not downplaying it, even if we have to admit that it is eerily, strangely beautiful to watch. Because it really does look like the mythical underworld has exploded out of the ground and spilled into the world. But we're also amazed that it has left so few injured or killed. How is this possible? Well, it's partly a matter of luck, but it's also partly a matter of the fact that we knew it was coming, or at least we suspected it was coming, because there were signs. And it's thanks to our understanding of how volcanoes work and how the underlying geology works that we can react so quickly and effectively, at least in the United States. For a month before Kilauea erupted, there were over 600 small and medium-sized earthquakes in Hawaii, and the volcano's main cone, Pu'o'o'o, had begun to literally swell up. See, the volcano's crater, a big hollowed-out bowl atop the mountain, was filled with a lava lake. And we want to point out that most volcanoes aren't literally holes in the tops of mountains filled with bubbling lava. Usually the crater is plugged up with solid rock. Sometimes it's even filled with water. And we'll get to why in just a moment. So picture it, a crater filled with semi-solid lava, pale orange veins running between dark masses of solidifying rock. And now picture someone inflating it from underneath. It starts to rise like Hades is making a terrible souffle. Well, that's what was happening. And that's how geologists knew something big was coming. And they were watching. Geologists in Hawaii are always watching, because Hawaii is covered with volcanoes. It has 5 volcanoes that are classified as active, which means they can actually erupt across its islands. Now, 2 of them are dormant. That means they could erupt, but they haven't shown any signs of erupting recently. 2 others have erupted in the 20th century, but have been pretty quiet otherwise. And one, Kilauea, has been erupting off and on since 1983. Yes, it's been erupting for 35 years. In point of fact, the current eruption is simply the continuation of one long 35-year eruption that occasionally takes short breaks. So yeah, they were watching. Volcanoes are just a part of Hawaii. Kilauea has erupted over 60 times since Hawaii was first settled in the early 1800s, and volcano imagery features heavily in Polynesian legends and folklore. And the various islands of the Hawaiian chain were all formed by volcanoes. In fact, each one is basically just the top of an undersea volcano sticking out of the sea. And when we say that, we mean each island is the top of the same single volcano. All of the volcanoes, the 5 active ones, and the dozens more that are inactive across Hawaii, they are all one volcano. And they shouldn't be there, because they are in a place where no geologist would ever have expected a volcano to be, let alone dozens. And if not for the fact that we live on a planet with liquid water, Hawaii might actually be the largest mountain in the entire solar system. But it had to concede that prize to a mountain on Mars, one that formed in precisely the same way as Hawaii, but it remained one giant volcano, because of no water. But we're getting ahead of ourselves. First, let's talk about why volcanoes that aren't Hawaii happen. That will also help us eventually understand why Hawaii happened, as long as we also talk briefly about submarines in the 1940s and novelties in the 1960s. But we have to go back to 1912 and some earth science weirdness that really baffled a geologist named Alfred Wegener. Wegener was born in 1880 in Berlin. His father was a wealthy teacher and pastor, and as a result, despite being the youngest of 5 children, Wegener was quite well off and received a very good education. He showed an aptitude for science, studied at university, and began pursuing a PhD in astronomy. But in 1905, he gave up astronomy. He feared there was nothing interesting left to discover there, and he thought he'd do better in studying climatology and meteorology. And as he traveled around the world studying the world's climate, he also began interacting with geologists and archaeologists. As he did so, he discovered that there were some weird patterns in the world's fossil record. See, as you dig down through the earth, you're digging back in time. Rocks form in one age. They are gradually covered with different deposits. Those become rocks, and then they are covered up, and so on. And as the Earth's climate has changed and geological events have taken place, the types of rocks that form in different places change as well. So each layer is a snapshot of a particular age of the Earth's geological history, at least in a given region. And when you add in the fact that animals are constantly dying, their bones and bodies are getting buried by the same processes, there's also a vertical timeline of the things that have lived on Earth through each age as they're buried in the ground. That's partly how we know the dinosaurs lived between 225 and 65 million years ago and then died out, because all of their fossils are in those geological layers. But as archaeologists and geologists were able to travel the globe more efficiently and effectively, they discovered something odd. Different places on Earth had the same geological history, like exactly the same. South America and Africa, for example, had a lot of the same types of rocks and the same types of fossils at exactly the same places. If you took a vertical sample from each, you couldn't tell the difference. And that's weird, because geological history varies heavily by region, and life evolves differently in different places. The only way that would make any sense at all would be if Africa and South America once touched each other. But there's a gigantic ocean in between. And Wegener, intrigued by this, did something that no other geologist had apparently ever done. He looked at a map. He noticed that Africa and South America fit together. The bulgy part of South America that holds Brazil could nestle perfectly into the concave western coast of Africa, so that you could walk from, say, Fortaleza, Brazil, to Tembe, Nigeria, in a few minutes. And so he developed a theory. Somehow, in some way, all of the continents had been mashed together into one big supercontinent. He called it Pangaea, the Everyland. And then they drifted apart. And he called it the theory of Continental Drift. And people thought he was bonkers. How could the continents, the solid surface of the Earth, drift? How could they move? That was insane. Wegener never gave up on his theory. He never proved it either, though he continued to search for some proof, some mechanism that could explain it. Each time he thought he had something, it was disproven, and his humiliation deepened. In 1930, he disappeared in Greenland while on an expedition searching for evidence of his theory of continental drift. A year later, his brother Kurt followed him to Greenland, trying to find some sign of Wegener. And what he found was Wegener's grave. He'd been buried by a partner after suffering a heart attack. The partner had never made it back to base, though, and his body remains lost to this day. If he'd survived just a little longer, he'd have had the missing piece of the puzzle. He just needed to join the British and US navies in their hunt for submarines during World War II. Submarines are actually older than you might think. A submarine is, of course, a naval vessel designed to travel under the water rather than across the surface, and they are extremely useful in warfare because by going under the water, they can't be seen from the surface. According to legend, Alexander the Great was the first human ever to sit in a submarine. He had a glass container constructed for him in 332 BCE so that he could be lowered into the water and study fish. Because Alexander didn't do anything small. No mere goldfish bowl for Alexander of Macedon. Not even an aquarium would do. At least, so the story goes. It wasn't until 1578 that anyone revisited the submarine idea. An English innkeeper, gunner, and mathematician named William Bourne devised an ingenious set of formulas to describe how, if you changed the volume of a ship but kept the mass the same, you could make it sink. He wasn't sure how to actually do that given the technology of the time and the fact that shrinking entire ships is sort of impossible. But then, Dutch inventor Cornelius van Drebbel had a different idea, one that didn't involve non-existent shrink rays. In 1620, he built an enclosed 12-person rowboat with an elongated fin-like attachment on the front. As the boat was rowed forward like a wing working in reverse, the boat was forced underwater. A few years later, Louis Dasson invented the Rotterdam boat, which was basically the same thing, but repurposed as an underwater battering ram that would punch a hole in a ship. And there were other attempts and failures. It wasn't really until about 1861 in the American Civil War that submarine warfare really got started. Both the American North and the South built several prototype submarines. But other nations, especially the English, were highly resistant to pursuing submarine warfare. In the early 1900s, the British Admiralty considered submarine warfare to be dishonorable and underhanded. They insisted it had no place in modern warfare, and they refused to fund it. Unfortunately for them, other countries, like Germany, didn't share that view. Submarines became a major factor in both World War I and World War II, and the Germans made especially good use of them. And so it was that the American and British navies found themselves in World War II desperately attempting to find ways to detect submarines underwater. And among the many technologies they developed, one of the earlier devices was basically a sensitive magnet on a string. Well, it was a little more complicated than that, but that's how it worked. You dangled the device below a ship and sailed around. And the force on the magnet would change if a large metal object passed under the ship. It wasn't particularly effective, and it didn't last long, but it did have one unusual, unforeseen side effect. It provided the first evidence that maybe Wegener hadn't been wrong about continental drift. As the ships passed back and forth over the Atlantic, their magnetic devices occasionally experienced strange oscillations for no reason. They were registering slight changes in the magnetic field below the ship, and they were at pretty regular intervals across the Atlantic, if you sailed east to west anyway. Moreover, they were symmetrical from the center of the Atlantic Ocean. If you mapped the areas of changing magnetism, you'd get a sort of barcode stretching across the Atlantic. Well, two barcodes, mirror images, stretching from the center of the Atlantic outward. It was weird, and it took many other surveys and many other years to figure out what was happening and why. What you have to understand is that there is iron locked in the rock in the surface of the Earth, and bits of iron act like little magnets themselves. And when the rocks form, those bits of iron align themselves with the Earth's natural magnetic field, which we've described before, like in our episode about Dead Reckoning. They organize themselves along the same lines of force that make compasses point north. But what you may not know is that every 450,000 years or so, the Earth's poles swap. That is, the magnetic field reverses, so that north is south and south is north. It's called geomagnetic reversal, and it's complicated. And since the iron in rocks aligns itself with that field when the rock is formed and then gets locked into place, well, it can be tricky to picture. But imagine this. Imagine there's a place where new rock is forming and then spreading out. New rocks form, the iron gets locked into alignment with a magnetic field, and then more new rock forms, pushing the old rocks aside. And every so often, the magnetic field changes, which means the iron aligns itself in the opposite direction. You would have stripes of rock with slightly different magnetic properties spreading out from the center. What the data showed is that new rock was forming in the middle of the Atlantic Ocean and then spreading in either direction. The Earth was constantly forming new crust in between the continents, and the continents were being pushed apart. Bingo. All of this, along with a lot of other complicated things like studying rock and meteor samples and tracking earthquake waves as they reflect around the inside of the Earth. And in 1977, we had the theory of plate tectonics. The Earth's surface was like a cracked eggshell. It was broken into 7 major areas called plates and a bunch of minor ones. And they were all moving. In some places, like at the Mid-Atlantic Ridge, they were spreading apart. That's called divergence. And at places like the Marianas Trench and the Himalayan Plateau, the plates were crashing into each other, converging. And at places like the San Andreas Fault in California, they slide against each other. That's called a transform, from the mathematical term for moving something around without changing its shape. Which is pretty funny because that is literally derived from Latin meaning to change shape. But we digress. The theory of plate tectonics explained a lot of things. Obviously, it explained Wegener's continental drift and the aforementioned seafloor spreading. And the theory also explained how the Earth's crust, its surface layer, is constantly renewing itself. At places like the Mid-Atlantic Ridge, magma is bubbling up from inside the Earth, cooling and forming new rock. At places like the Marianas Trench, where one plate is crashing into another, one plate gets forced down below the other. As it gets forced deeper into the Earth, the rock melts and joins the magma down there to get recycled as new rock. It explained earthquakes as the motion of plates grinding against each other. It also explained the formation of many mountain ranges and other geological features. For example, the Himalayan mountains are the result of 2 tectonic plates colliding and buckling and folding. Now, we should mention that all of this happens very slowly. Tectonic plates move less than half an inch a year on average. This stuff all happens over the span of geological time, not the span of human lifetimes. There are no great cataclysmic collisions that form massive mountain ranges overnight. It takes ages for the ground to buckle and grind itself into new mountains. Volcanic eruptions notwithstanding, of course. And that geological timescale is very important to understand the nature of what's under the crust and how plate tectonics are even possible. Because I guarantee you, it isn't as liquid as you think. I bet right now you're picturing a shell of thin rock over a bubbling, soupy morass of melted liquid rock, aren't you? That would make sense, wouldn't it? But it just isn't the case. So let's lay it out. Obviously, the surface of the Earth, the crust, is made of solid rock. Those are the tectonic plates, and they're about 20 miles thick, though it varies a bit. Below that, stretching down between 20 and 1,800 miles, is the mantle of the Earth. And then, from 1,800 miles down to almost 4,000 miles at the center is the core of the Earth. Now, the core of the core is solid iron. Despite the tremendous heat down there, it's solid because the tremendous weight of the entire planet keeps it compressed into a tight, solid ball. Around that inner core is an outer core that consists of liquid iron and nickel. And then you've got the mantle. The mantle is primarily rock. It's mainly silicon and magnesium with some aluminum and other trace elements in there. And despite the tremendous temperatures, the mantle is also pretty much solid rock. The tremendous pressure keeps it that way. Except the mantle does contain something that is pretty unique to Earth. At least in this solar system. At least at the highest levels. The upper portion of the mantle, known as the asthenosphere, has trapped in it a very small amount of water. Like a really small amount. But just enough. And the pressure is slightly lower there because it doesn't have an entire planet sitting above it, just a thin crust. And those two factors, the slightly lower pressure compared to the rest of the mantle and a slight lubricating effect caused by trace amounts of water trapped in the rock, make the otherwise solid rock very, very, very slightly plastic, slightly viscous, slightly liquid. If you consider it over the very, very long time scale of geological time. And that means that it can, very, very slowly, flow due to differences in temperature. Just like the atmosphere and the ocean, it has currents, and those currents drive the motion of the tectonic plates. Of course, where the plates collide, you do get tremendous heat differentials. And those are enough to melt the rocky crust and upper mantle into something a bit more liquid, magma. And that magma can gather in pockets under the crust. And when weaknesses and cracks in the crust allow, it can start oozing its way to the surface. And that's how you get a volcano. But plate tectonics and geological forces only describe the forces that plant the seeds for volcanoes, and why they happen where they do. But what happens when a volcano actually erupts? And how is it that the Hawaiian Islands can be so volcanic despite the fact that they are in the dead center of a tectonic plate and not in a collision zone? And what does this have to do with the largest mountain in the solar system? Well, next week we'll talk about the other half of this puzzle. We'll talk about lava. This has been GM Word of the Week. It's written and researched by the Angry GM and produced by me, Fiddleback. You can support us on Patreon at patreon.com/GM Word of the Week. You can find more at gmwordoftheweek.com and theangrygm.com.